Hello, everyone. So I'll be presenting my summer work as a research scholar at Auton Lab, and we worked on Bayesian framework for decisions under uncertainty with vision language sensors. So our problem is motivated by DARPA Triage challenge. DARPA Triage challenge is where robot swarms try and detect casualties, and each robot has a vision language model that says something about the casualty. And the challenge is there's a limited bandwidth and visibility, and the stakes are high because it's a safety critical environment during triage, and it requires robust modeling, and there is no training data for us to learn uh, the actual mapping due to the lack of limited data. And how do we make decisions under such high stakes and uncertainty? That's what motivates our project. We first define the structure of the problem based on the DARPA's provided rubric, and we define the structure of the data based on the BaseNet first, and this is provided by the rubric, and then that helps us define the structure even when there is limited data. And this is our BaseNet. And how do we make decisions based on the responses of VLMs, the vision language models? We found out that vision language models are overconfident even when you remove the evidence. So, for example, when this person's face is blurred increasingly, even when the evidence is removed, VLMs are responding very confidently about whether this person is smiling or not. And this motivates us to find some other reliability measure on the answers that are provided by vision language models. We looked into models internal as well. For example, when we compute the entropy of the softmax at the answer token, we can sometimes predict whether the answer is correct or not. So if a model responds with a higher uncertainty, then the answer is likely going to be wrong. And this does descent. We could also probe the hidden layer and train the linear probe on detecting whether the answer will be right or wrong. And that also does perform decently, and that helps us understand whether a VLM's answer is reliable or not. But this is not enough because this comes from models internals, and we need something else. So when these are the motivations for our model, this is the entropy that we discussed, and this is the visibility. So our idea is that if a model doesn't see the relevant evidence, then that means it might likely not answer accurately. So is since the models are overconfident, so providing that external factor that are beyond the model's internals might help us predict reliably whether VLM's answer are correct or not. And that motivates us to look into external factors such as visibility, which is the fraction of the relevant reason visible to that robot sensor at that particular instance. And we found out that the visibility of the relevant reason that are coming from the external factors, this is not correlated with answer token entropy. That means that models external, some external factors that come outside of model and models internals, they give complementary different signals, and we need to find a way to use both of them in predicting whether the VLM's responses are correct or not. This motivates us to build a reliability model, and this is the definition of the model. For each reading, we add a weighted log likelihood ratio, and this enters as a virtual evidence instead of the hard evidence. And we fuse the views in the additive log odds, and this is the main part that we work on. And then this generalizes to single view or multiple views because we are treating each view as an evidence, and then we are providing multiple of those evidence, and those add in the additive log odds. And then since, let's say, we have similar views that are correlated, then we have to somehow temper those correlated views, because they will push the evidence in one direction when you have multiple things that are correlated to each other. And this provides us a general way, and then we build our framework on top of this a general way of fusing evidence. And this is the framework we propose. Let's say we are answering a question about a casualty, and we have vision language sensors at different angles that are seeing different parts of the same reason. Let's say we ask, is there a trauma in the head? And we have to make a decision based on that. So first we break that, is there a trauma in the head, into more easier questions that are easy for VLMs to answer. For example, is there blood, or is there a wound? Uh, are those atomic cues that are answered by VLMs more reliably than the abstract questions? And this helps. And we put these atomic cues as evidence at children to the main trauma head node in our BaseNet. And that way, first we fuse the atomic questions, and then after we provide evidence from these atomic questions, then each view gets its own evidence, and which is regulated by models internal and external. So whether the VL, how much does each view count, is first comes from models uncertainty, models internal. So if the model is certain, then we provide it higher weight. And then we also use the external geometry factor, how much of the relevant reason is visible, so that a view that didn't see anything in the relevant reason doesn't contribute much. And then we add the log likelihoods. And then finally, we optimize on the utility, because in real world sometimes the loss is asymmetric and there are different things we want to prioritize. So instead of just reporting on the posterior, we report on the utility that we care more about. And we test our framework on multiple data sets. First, we test it on 6 different benchmarks, and 2 of those include our DARPA Triage challenge data that come from the field itself. And we find out that our Bayesian Fusion framework beats the naive baselines, as well as majority voting, as well as confidence weighted vote, and it performs similar in some places to more stronger baselines. For example, picking the most optimal view if we knew that in advance, or picking the or using different methods of pooling and selection. And at the bottom is our proposed framework that uses external geometry and models internals with our model under different ablations. And it seems that the pattern indeed generalizes to other data sets. So the limitations of our work is that right now, as I mentioned, the correlated evidence still needs some work. We might need to use the entire correlation metrics instead of one number, or ICC. And so we need to find more robust ways of tempering the correlated evidence. And then we also need a way such that the reliability generalizes. So right now, if we were to test a new sensor, then we're not sure if our lambda that is fitted per sensor generalizes if we use a different vision language models. And it would be nice to have something that transfers across different models. And then finally, we would like our framework to be tested on different domains, since for now we have tested it on vision language models, but the Bayesian framework that we propose can be generalized to other tasks apart from just vision language models. And we'd love to test how that adding addition of evidence and tempering logic we provide how that would generalize to different domains, because in each domain, a domain expert can create atomic labels and that are based on their domain expertise, and then fuse them using our framework. And they can also do some ablations on those. And then finally, the utility is also specific to different tasks. So a utility in different domain might be different. So the experts in that reason have the ability to define that utility and do the ablations and use our framework. And that's one next step for us to test it on a different domain. And that was the end of the slide. And thank you so much for listening. And I'm very grateful to Riz and Auton Lab and the DTC team for the support. And have a good day.